Hello everyone, I'm Kairi Furui from OA Laboratory, Department of Computer Science, School of Computing, Tokyo Institute of Technology in Japan. Today, I'd like to talk about my presentation titled Compound Virtual Screening by Learning to Rank with Gradient Boosting Decision Tree and Enrichment-Based Cumulative Gain. Let's start with the background of my research. The development cost and time required to make a new drug are increasing year by year. So it is important to reduce these costs, and virtual screening has been used to solve this problem. Virtual screening is computational search for active compounds against a target protein from an extensive compound library. So it is essential for virtual screening to rank to the top prediction properly. If we consider virtual screening as a ranking prediction, learning to rank is applicable since learning to rank is one of the machine learning tasks that runs ordinal relationships. Learning to rank is a machine learning technique widely used in information retrieval, and it has recently been applied to the problem of ligand-based virtual screening, LVVS. Using learning to rank has two advantages for LVVS. First, learning to rank is suitable for ranking prediction. Second, learning to rank is less sensitive to environmental differences among assays. Biochemical affinity indices such as IC50 vary widely from one assay system to another. In regression, it is difficult to integrate assay data from different environments. On the other hand, as shown in the figure below, learning to rank does not predict values directly, but it runs only ordinal relationships separately from different environments. Our research in learning to rank has two motivations. First, we applied GBDT-based ranking models to virtual screening for the first time. GBDT, gradient boosting decision tree, is found as a machine learning method widely used in machine learning competition, and the algorithm is to improve prediction accuracy by boosting decision trees sequentially as shown in the figure below. A learning to rank method called lambda map has been broadly used in information retrieval in recent years. Lambda map is a machine learning method for which combines a gradient boosting decision tree and ranking loss function. Existing studies mainly use rank-SVM. Rank-SVM is one of the most common learning to rank method, but lambda map may be better for virtual screening. The second motivation is that ranking metric NDCG does not represent the extent of improvement in predictions. NDCG, normalized discounted cumulative gain, is a ranking metric. NDCG was used in previous study of LVVS. NDCG is a metric designed for virtual evaluation of learning to rank performance in information retrieval. As shown in the figure on the right, NDCG considers the top of the ranking prediction to be important, and it is also important for virtual screening. However, we cannot know if the NDCG value alone is better or worse than a random prediction. For example, the right figure, if there were only ranking V, it is unclear whether 0.58982 is good or not. So NDCG may be inappropriate for virtual screening. In LVVS, the degree of improvement is important, such as enrichment factor and ROC-AUC. So a ranking metric suitable for virtual screening is required. Here's our proposal. First, this study tried to use the GBDT model with ranking loss functions called lambda rank and lambda loss in LVVS. And we proposed our new ranking metric, NEDCG, normalized enrichment DCG, aiming to properly evaluate the goodness of ranking predictions. The results were as follows. First, the GBDT-based ranking model outperformed the conventional ranking model, and NEDCG was helpful for a more direct assessment of compound screening performance. Now to the main part of presentation. I'll explain the ranking metrics DCG, NDCG, and NEDCG. Discounted cumulative gain DCG evaluates the extent to which active compounds are listed in the top K predictions. Because the top of the prediction is important, it is suitable for the evaluation of virtual screening. Normalized DCG, NDCG is DCG normalized to be 1 when the predictions are in the correct order. However, NDCG value itself is meaningless and can only be evaluated compared to the other models as mentioned above. Therefore, we proposed normalized enrichment DCG, NEDCG. NEDCG is NDCG modified to be 0 for random predictions and 1 for correct predictions. This means it evaluates how variable our prediction is for virtual screening. I'll explain the advantages of NEDCG over NDCG. In the two rankings A and B, NDCG is 0.75 and 0.287. However, in this ranking prediction, even if the prediction is made randomly, the score is 0.386. This random NDCG varies from case to case, and we should consider it. NEDCG removes these random biases for ranking A, 0.590, and for ranking B, minus 0.161. It means NEDCG evaluates how variable a random ranking prediction. Here are two ranking loss functions. I'll explain the details of formula, but lambda rank and lambda loss are similar. Lambda rank and lambda loss computes the pairwise loss for all comparable elements and also gives the penalty regarding NDCG. Lambda rank penalizes NDCG changes, and lambda loss minimizes NDCG cost. We used two datasets with different objectives. Dataset 1 is PDE, phosphodiesterase family dataset, IC50 collected from Campbell. It contains 21 proteins and about 10,000 cases for training. This is a difficult case to treat as a regression task because they contain various assays and multi-proteins. Dataset 2 is the risk-based dataset for the inhibition rate. It contains 10,000 cases for training. This is a single assay and same protein, and it is a common compound screening cases. These are examples of compound in each dataset. This is the summary of experiment. We evaluate the if GBDT by lambda rank and lambda loss. For comparison, we use the GBDT with regression and existing learning to rank model, rank SVM. As for features, For compounds, we used 1 or 2-dimensional compound descriptors by the modelet. For proteins, we used the normal Smith-Waterman score with the target in training data. First, here's the result of the complicated task of Dataset 1. The left is existing NDCG, and the right is proposed NEDCG. X-axis is the number of top cases, and the y-axis is the corresponding matrix. Two results show the lambda loss and the lambda log. The red and pink lines outperforms existing rank SPM and lambda regression. In addition, as shown in the figure on the right, the NEDCG of regression is below 0. This means that it was a random prediction. NDCG only shows the relationship between models, but the result of NEDCG reveals that the regression is inappropriate for such a task. Next, here is the result of simple task of Dataset 2. The result that those figures shows that learning to rank and regression have no significant difference. This indicates that learning to rank is less effective for single assays such as Dataset 2. And NDCG and NEDCG have similar results, so NDCG is good enough for such a simple task. Following discussion. As shown in the result, learning to rank was less effective in complicated tasks, but to a limited extent. So our conclusion is that the ranking prediction should be used as an alternative when regression prediction cannot achieve practical accuracy. And the decision should be based on evaluation that considers the randomness effect, such as proposed NEDCG. Here's the conclusion. First, the GBDT-based ranking model outperforms the other models. Next, the ranking prediction should be used as an alternative. Finally, the proposed NEDCG provides a more intuitive evaluation. The future work is that we aim for higher performance by utilizing deep learning models or improving the GBDT model. And learning to rank may apply to other chemoinformatics tasks such as ADMET, QSAR, and drug-target interaction prediction. That's all. Thank you very much for your attention.